Hello everyone, welcome to this class on finite element analysis, and in this class let's study this problem. Evaluate eigenvalues and eigenvectors of the longitudinal vibration of the constrained uniform circular bar shown in the figure. Take minimum two elements, take E equal to 210 gigapascals and mass density rho equal to 7860 kg per meter cube. And here this is the figure that is given. That is a bar where it is fixed on one side and its length is given as 0.25 meters. Its diameter, that is, it is given already as a uniform circular bar. Therefore its diameter is given as phi, that is 0.02 meters. So now let's try to write the given data first. So given data is nothing but E equals to 210 gigapascals. So giga in the sense it is 10 to the power of 9. So pascals, okay. So 200 into 10 to the power of 9 pascals can also be written as 210 into 10 to the power of 9 newtons per meter square. So it is understood clearly. So, and they are also telling in the problem to consider two elements. Therefore, when considered for two elements, E1 and E2, both it will be this E itself. So we can take E equal to E1, E2. That is nothing but 210 into 10 to the power of 9 newtons per meter square. Then D is nothing but diameter, but here it is given as phi. Therefore, phi1, phi2, if it is divided into two elements, it's going to be the same, 0.02 meters only. It's not going to change. And L1, L2, see there is only one length given, but they have given in the question as take minimum two elements. Therefore we have to divide it as two elements. Therefore 0.25 divided by 2 will be 0.125 meters. Apart from that, rho is nothing but mass density. So because here in this problem we are going to find mass matrix, so therefore we need this rho in the form of mass density, because sometimes if it is given as Newton per meter cube, then you have to divide that value by 9.81 to get this rho, that is kg per meter cube. So check for the SI units, it is in kg per meter cube. So in this problem let's try to keep all the units, all the parameters into common unit, that is meter or meter square, something like that. So here it is converted into Newton per meter square, here it is in meters, here it is in kg per meter cube. And here when you are trying to find the area, that is A1 and A2, area is nothing but pi by 4 into d square, that is pi by 4 into 0.02 square. So when you are doing that, you are getting the answer as 3.14 into 10 to the power of minus 4 meters square. Therefore area 1, area A1, area A2. So we just found it. So in this problem we have like few steps. There are you get marks for every steps how much ever you solve. So the first step is FEA model. So FEA model is quite very simple. This bar is divided into two elements, minimum two elements, that is the first element and second element. Here you can just see it. So therefore it is also divided into two equal elements. Therefore 0.25 divided by 2 is 0.125 and 0.125. So both you have to divide it. So that is something but element number 1 and element number 2. So element E1, element E2, it is written in small e1 and small e2, and length L1 equal to 0.125 meters and length L2 equal to 0.125 meters. So nodes 1, 2 and 3. So 1 and 2 corresponds to element 1, 2 and 3 corresponds to element 2. So what is the second step? Second step is nothing but elemental stiffness matrix. So the elemental stiffness matrix for this kind of problem, this is a bar element. For a bar element, the formula is going to be K equal to AE divided by L, 1 minus 1 minus 1 and 1, where A is nothing but area, E is nothing but Young's modulus, L is nothing but the length. Therefore for element number 1 it is going to be A1 E1 by L1, 1 minus 1 minus 1 and 1. So what is the value of A1? A1 is nothing but, so A1 is nothing but 3.14 into 10 to the power of minus 4, that is written here. And the value of E1 is 210 into 10 to the power of 9. So it is written, it is interchanged, that's it. Apart from that we have L1 is 0.125, it is given over here. It is nothing but, so upon solving all this we are going to get 0.53 into 10 to the power of 9, 1 minus 1 minus 1 and 1. So it's fine even if you don't multiply this 0.53 inside this matrix. The reason is, suppose even if you are multiplying it, while you're calculating the global stiffness matrix, it could be little difficult. So you can leave it as it is. But the thing is, even in K2 you have to get the same number. Only then it is fine. Only then it is possible without multiplying. If you are getting a different value, then you may have to multiply it. Okay, now let's try to find K2. In K2, the value of A2 is not going to change. The value of E2 is not going to change. The value of L2 is not going to change. So that is the reason why we are not multiplying, because while finding the global stiffness matrix, you can simply write this outside and just add this inner element. So it's going to be very easier. That is the reason why we are going to leave it as it is. So please understand that. So next, let me go to the element stiffness matrix for element number 2. So for element number 2, when I'm going, K2 is nothing but A2 E2 by L2. So all that we have. So the value of A2, that is area, is going to be 3.14 into 10 to the power of minus 4. The value of E2 is 210 into 10 to the power of 9. The value of L2 is 0.125 meters. So upon solving that, we are going to get the same answer. That is the reason why we are writing it outside, because multiplying it inside is going to take too much of time, and when you're doing this global stiffness matrix, it could be a bit difficult to add all those elements. So that is the reason. That's why I've written it here. 0.53 is not multiplied inside the matrix because the values of A, E and L are same in both the stiffness matrices, and also it is done to make the addition of global stiffness matrix easier. So because you know the value of area is same in both the cases, the value of length is both same in both the cases, the value of E is also same in both the cases. That is the reason why we are not doing it, because we are going to get a same common value. While you're doing in the global stiffness matrix, you can do it very easily. You can add 1 plus 1 2 easily, something like that. So while the global stiffness matrix comes, you can understand it better. The third step is nothing but mass matrix for element 1 and 2. That is, mass matrix is given by rho AL divided by 6, 2112. Even this is a formula for a bar. For a bar, this is going to be the formula. Suppose if it is a truss or a beam, the formula is going to change. But in the exams, mostly they ask bar problems. So this is the formula. That is M equal to rho into A into L divided by 6, 2112. Suppose if you are doing it for element 1 and 2, rho 1, rho 2, density, mass density is going to remain the same. A1, A2 is going to remain the same. L1, L2 is going to remain the same. So while after substituting it, the values of rho 1 and rho 2 are 7860. The values of A1 and A2 are 3.14 into 10 power minus 4. The values of L1 and L2 are 0.125. So upon solving it, you are going to get this. Even here also, you are not going to multiply that 0.05 inside. The reason is to make the global stiffness matrix addition very easier. That's what I have written it in the note here. You can just read it out. So just better, so try to make the calculations, try to make the simplification as easier as possible, because you have lot many steps and it may take too much of time. So just to avoid the time, we have to do it. So next let me go to this global stiffness matrix. So global stiffness matrix K equal to K1 plus K2. That is K equal to, now if I try to add, so let me just take this, so you can just see 0.53 into 10 power 9 here, and even here also 0.53 into 10 power 9. That's going to remain common. So you're going to take that 0.53 into 10 power 9. And this one, I think all of you must be knowing it by this time, to add the global stiffness matrix. So at nodes 1, node 2 and node 3. Similarly at node 1, node 2 and node 3. So upon adding it, you will get it. I don't think I have to give you a detailed explanation regarding the global stiffness matrix. Even if you need a detailed explanation how to add the global stiffness matrix, you can watch my previous videos on it. The next one is global mass matrix. So global mass matrix, nothing but this M1 plus M2. So already we have found M1 and M2. So you are going to take 0.05 common. So apart from that, you see 0.05 when you're taking common, you have like when you're trying to add all that. So at nodes 1, 2 and 3, at nodes 1, 2 and 3, this is going to be the answer. Even here also it's going to be the same. The addition is not going to change. So I don't think I have to give you some very good explanation about this, because already in many of my previous videos you can just better watch it. So this is how you are getting global stiffness matrix and global mass matrix. That is, global stiffness matrix is K1 plus K2 and global mass matrix is M1 plus M2. The next step is, see, in this problem we are going to find the eigenvalues and eigenvectors. So now let's try to find the eigenvalues. The eigenvalue problem is given by k minus lambda m into x equal to 0, or when you're trying to multiply this x inside, we are going to get k into x minus lambda into m into x equal to 0. So what is k? K is nothing but the global stiffness matrix. You're going to write that as it is here. And x is nothing but the displacements. So x is nothing but the displacements. We have 3 nodes in this problem. So let me just try to take you to this first step, that is FEA model. At node 1, node 2, node 3, we have three displacements. That is represented by Q1, Q2 and Q3. So let me even write that here. So that will be much helpful. So at nodes 1, 2 and 3, we are going to get the displacements 1, 2 and 3. That's what is mentioned here as Q1, Q2, Q3. So that is nothing but k into x minus lambda. Lambda you're going to write it as it is, and the value of m is nothing but the mass matrix. So mass matrix is given over here. We have found out that is the global mass matrix. 0.05 is taken outside. So before that lambda itself, I'm going to write that, because you're not going to write it as lambda 0.05. Instead we can write it as 0.05 lambda. That will make some sense. and after that we are going to write this matrix as it is. Then again x is nothing but q1, q2, q3, the displacements. It is nothing but going to be 0. And in this problem, let's clearly see that node number 1 is fixed. So node number 1 is fixed. So as node number 1 is fixed, we are going to eliminate the first column and first row, first column and first row in both these matrices. So once after doing it, we are going to, we are left out only with the other elements. So what we have to do is, we have to take it like this. That is, we have to apply the boundary conditions, and after applying the boundary conditions, you have to take this one. Determinant of k minus lambda m equal to 0, or that can also be written as in this format. That is, instead of brackets, you are going to put it as, replace it with two lines. That is, determinant of k minus lambda m equal to 0 in two lines. So k minus lambda m equal to 0, that's all, only that you are going to take, and you are going to leave this x, that is q1, q2, q3 you are not going to consider. Now while doing that, see, we have eliminated this first row and first column, first row and first column in both the cases. Apart from that, just see what are the elements that are present. You see, now I am going to explain this clearly for you. 0.53 into 10 to the power of 9 into 2, 0.53 into 10 to the power of 9 into 2, minus, because we have to do k minus lambda m. So understand that clearly. This is k, this is lambda, this is m. Only that we are going to consider after eliminating the first row and first column. So k is nothing but 0.53 into 10 to the power of 9 into 2. So 0.53 into 10 to the power of 9 into 2, that is nothing but k, minus lambda. So lambda I have written it here. But please understand that lambda you are not going to write it at the beginning, because you can't say it like lambda 1, lambda 2. Instead you can say 1 lambda, 2 lambda, because first we are going to write the constant. So lambda we are going to write it later. Minus 0.05 into 4. The corresponding elements in each of the matrices you will have to add. You will have to multiply and add all that. That is only very important. 0.53 into 10 to the power of 9 into 2, minus, because this is not there in this k minus lambda. So just consider this is this determinant is what I'm going to consider for the, after eliminating the particular row and column. The next one is minus 1, or 0.53 into 10 to the power of 9 into minus 1. It's nothing but going to be minus, simple. You can just take it simple. 0.5 minus 0.53 into 10 to the power of 9, because that minus is multiplied over here. Therefore 0.53 into 10 to the power of 9 minus 0.05 lambda into 1, 0.05 into 1 into lambda. So into 1 into lambda, we are just going to write it like this. Next, let's go to the next one. 0.53 into 10 to the power of 9 into minus 1. So minus, you are going to take it outside. You are going to get minus 0.53 into 10 to the power of 9. Minus, this minus is going to be written here. 0.05 into 1 into lambda. That's what is written. Next, finally, you have this last one, 0.53 into 10 to the power of 9 into 1. So into 1 will not be written so clearly, because it is already understood. Minus 0.05 into 2 into lambda, into 2 into lambda. So now what we are going to do in the next step, you are going to multiply these numbers. You are going to leave the exponents as it is. 0.53 into 2 is nothing but 1.06 into 10 to the power of 9, minus 0.05 into 4 is nothing but 0.2 lambda. Here we have minus 0.53 into 10 to the power of 9, minus 0.05 into 1 is 0.05 itself, lambda. And here minus 0.53 into 10 to the power of 9, minus, that is going to be written as it is, minus 0.05 into 1 is nothing but going to be 0.05, and lambda is going to be retained it as it is. And here we have 0.53 into 10 to the power of 9, minus 0.05 into 2 is nothing but going to be 0.1 lambda. That is nothing but be equated to 0. Now what you have to do is, you have to solve this determinant. You know how to solve the determinant. You are going to multiply this diagonal elements. First this diagonal elements minus of the product of these two diagonal elements. So understand that very clearly. I have written that over here again. So let's try to solve the determinant here for you. So I have just solved the determinant to find the values of lambda 1 and lambda 2. Lambda 1 and lambda 2 are nothing but eigenvalues. So once you try to find out the eigenvalues, you're going to get, half of the problem is done there. You will get, suppose if it's asked for 10 marks, you will be getting 5 marks over there. So I've just written it over there, only this one. Only these four, these four elements I have written it out. So I've just written it out here, over here again. So 1.0, so all that I have, that is equated to 0. Now what I'll be taking, 1.0 Now let me try to consider these two elements. These two elements, let me try to write it over here, because let me try to explain you the determinant, I mean how to solve this determinant, because it is not an easy thing, easy terms here, because there are many terms involved over here. So we'll have to, this solving this determinant itself will take a longer time, because still here all the steps are easier, but even this step is easier, but it's very very lengthy. So let me try to write this 1.06 into 10 to the power of 9 minus 0.2 lambda into 0.53 into 10 to the power of 9 minus 0.1 lambda. Here let me try to consider this 1.06 into 10 to the power of 9 as A. Just try to assume it, minus the 0.2 lambda as B, multiplied by the 0.53 into 10 to the power of 9 as C, minus 0.1 into lambda into D. So let me try to take it like that, A minus B into C minus D. When you're doing A minus B into C minus D, what you can do is you can multiply this A separately to C as well as to D, and then this B separately to this C and there to D. So A multiplied with C is nothing but AC, A multiplied with D is nothing but AD, but plus into minus will be minus. Then B multiplied with C is nothing but BC, therefore minus into plus is minus. Minus into minus will be plus, B into D will be BD. So now what is the value of A? A is this 1.06 into 10 power 9, value of B is 0.2 lambda. It is not minus because it's only 0.2, because minus is minus, because here corresponding elements is what you have to take. Then C, the value of C is 0.53 into 10 to the power of 9, minus is going to remain the same, and the value of D is 0.1 lambda. So now while you try to multiply it, so this is nothing but A into C minus B into D, because it's sorry, A into D, A into C is here, A into D minus A into D is here, minus B into D, B into C is here, plus B into D is here. So I have already told you what's the values of A, B, C, D. Just by observing you will get it. It's not so difficult. So once you try to multiply this, I mean using your calculators, if you try to put it 1.06 into 0.53, just multiply these two numbers. 1.06 into 0.53 is going to be 0.5618. And multiplying this 10 to the power of 9 and 10 to the power of 9, you know that when bases are same, powers can be added. Therefore 10 to the power of 9 plus 9 is nothing but 18. 10 to the power of 18, you can try to write it directly. Then you have 1.06 into 0.1, that is written as 0.10106 lambda. Lambda is going to be written, then multiplied by 10 power 9. There is only one power over here, and minus 0.2 into 0.53, that is nothing but 0.106, and lambda is going to be retained as it is, into 10 to the power of 9, plus 0.2 into 0.1 is nothing but 0.02. Lambda into lambda is nothing but going to be lambda square. So now let me try to rearrange this equation. Once you try to rearrange this equation, first you can write this number where you have, or this term where you have the square. So I'm going to write it 0.02 lambda square. Then you can write the terms which has this lambda. So these two are having lambda, minus 0.106 lambda into 10 power 9 minus 0.106 into 10 to the power of 9. We are having like that, plus 0.5618 into 10 to the power of 18. So you are having that. So once you try to do that, what you get? You try to get this. Then 0.02 lambda square minus, when you're trying to, like these two numbers are going to be the same, so minus you can take it common and you can try to add these both. So minus 0.106, or you can just leave it. Lambda you can just leave it off. So if you just take your calculators, so let me try to take the calculators and just show you over here. It's nothing but, so let me just try to show you using the calculator. So 0.106 into 10 to the power of 9. So the same thing again, because if you're trying to take minus outside, if you take minus outside here, 0.106 lambda into 10 to the power of 9, plus minus into plus is going to be minus, plus this number, it's going to be the same number again, 0.106 into 10 to the power of 9. You don't put lambda over there. So if you just put it, you will get 2 into 10, 212 into 10 to the power of 6 can be written as 0.212 into 10 to the power of 9 also, because just trying to adjust the powers. So just try to shift the powers to the left hand side. So here in the calculator you may get like 212 into 10 to the power of 6, but just try to shift the powers to the left hand side. So you'll get 0.212 lambda into 10 to the power of 9. Or else even you can do like this, just try to put this number and multiply it by 2, because it's going to be the same number, plus this one. because this has to be written in the form of ax square plus bx plus c, in the form of a quadratic equation. That is the reason why we are doing all this. Then that is the first equation. Similarly, you can take the remaining two you can take it when you're considering that you are getting 0 minus 0.53 into 10 to the power of 9 minus 0.05 lambda. The same thing over here, minus 0.53 into 10 to the power of 9 minus 0.05 lambda. That can be considered, so you can just see clearly, it is nothing but the same equation repeated twice, a minus b into a minus b. A minus b into a minus b can be written as a minus b the whole square, which is nothing but a square plus b square minus 2 into a into b. So when you are trying to do it, a is nothing but this is minus 0.53 into 10 to the power 9, b is nothing but only 0.05 into 10 into lambda. That is, you will not get minus there. So therefore a square is minus 0.53 into 10 power 9 the whole square plus b square 0.05 lambda square minus 2 into a value is minus 0.53 into 10 power 9, b value is 0.05 lambda. So once you are trying to, what you can, if you just try to expand that, what you are getting is, so it's minus 0.53 the whole square is minus 0.20. It is actually going to be plus over here. I think I have made a mistake over here, because it's minus 0.53 the whole square is going to be plus. So I think I have made a mistake over here. So let me try to correct it over here. So I think I have just already solved this problem. So please observe here. I made a small mistake over here, because while you're solving, see that you try to observe correct that mistake. So into 10 to the power of 9 into 10 to the power of 9 is going to be 10 to the power of 18 plus this one 0.05 the whole square is nothing but 2.5 into 10 to the power of minus 3. Lambda into lambda is going to be lambda square. Then you have minus into minus plus 2 into 0.53 into 0.05. Multiplying all these numbers, you will get 0.053 into lambda. So into lambda, and 10 to the power of 9 is going to remain in the same. So on rearranging this equation, first you are going to write this lambda square wherever you are having that lambda square. Then you are going to write this 0.053 lambda into 10 to the power of 9. Then you are going to write this. So it's going to be plus over here. As I told, I think I have made a small mistake over here, because minus into minus is going to be remain plus. It's going to be plus. So I have already solved this problem. So the final answer could be a bit wrong, because here instead of plus I had taken minus initially. So next, let's go to the next step. The next step is nothing but going to be like we have already got the two equations. You can just see clearly over here in this page. Here we have got the first equation. So the first equation is obtained here. So this is the first equation. Then this is the second equation. Whatever we solved it just now was second equation. So both the equations you have to get it in a similar way. So in the form of ax square plus bx plus c. Now those two equations were obtained by cross multiplying this the terms in the determinant. Now what we have to do is we have to subtract them. Only when you subtract you get the final equation. So let me I have just taken it over here. You can just see clearly I have written it those equations again. But in the exams you can try to minimize your time by avoiding writing too many times. So I have just written that over here. So here it is mentioned as like this. So here it is actually, it must have been plus over here. As I told, I have made a mistake. Here it must have been instead of minus, it's going to, it should have been plus. And here while minus into plus is going to be minus. So here it should have been minus. But okay, just check the answer as of now. But you can try to do it when you're doing only that plus minus as that mistake has happened. The final answer may vary. But still, let me just try to go as per the answers whatever I have got. Okay, now when you're trying to multiply this ax square plus bx plus c, this equation minus this equation. So wherever you have lambda square, this one minus this term, you're going to write it separately. 0.02 lambda square minus 2.5 into 10 to the power minus 3 lambda square. You're going to write that separately. Minus this term 0.212 lambda into 10 to the power 9. Minus into plus is going to be minus 0.053 lambda into 10 to the power 9. Plus 0.5618 into 10 power 18 minus into plus is going to be minus 0.2809 into 10 power 18. So once you try to solve all that, here I can take lambda square common. When I try to take lambda square common, I'll get 0.02 minus 2.5 into 10 power minus 3 minus, and here I'll get, here you can just take lambda into 10 power 9 common. If you are taking that, you will get minus 0.212 minus 0.053. You are going to get minus 0.265 into 10 power 9 lambda. Plus here you can take 10 power 18 common, 0.5618 minus 0.2809. As I told, there is some slight variations over here, but once you try to solve that, you will get the answer. Let me just try to show it here itself. So So it is 0.5618 minus 0.280, 0.5618 minus 0.2809. So it has to be 0.2809. So let me try to change that answer. 0.2809. So we have just got that answer. So now I'm going to write that in the form of ax square plus bx plus c. So what's the value of a? The value of a is, it is already written in the form of ax square plus bx plus c. The value of a is 0.0175. X, in the place of x you are having lambda. Next, the value of b is, so it can be written like this, plus of this. Therefore it has to be written as minus 0.265 into 10 to the power of 9. Bx, x is nothing but lambda, plus c. The value of c is, I'll just strike it over and write it correctly now, 0.2809 into 10 to the power of 18. So once you try to do that, then you have to solve this quadratic equation. So solving that quadratic equation, I'll just show you using the calculator. So in calculators you can just click this mode. So here you're getting equation. Under equations you're getting like this, then you press this right side button, you're getting degrees 2 and 3. So let me just put degree 2. So let's try to enter the value of a, 0.0175, and the value of b is minus 0.265, minus 0.265 into 10 to the power of 9, and the value of c as 0.2809, 0.2809 into 10 to the power of 18. So into 10 to the power of 18. So the value is found to be, x value is found to be 1.39 into 10 to the power of 10. So let me try to write it correctly. So 1.39 into 10 to the power of 10. So the x is nothing but lambda 1. Similarly y is nothing but 1 point, so it is, let me just put it in engineering modes. So it is, I think it is 1 2 3. So you just clearly observe 1.146 into 10 to the power of 9, or 0.1146 into 10 to the power of 10. So 0.1146 into 10 to the power of 10. So these two values are nothing but eigenvalues. So once you try to get the eigenvalues, you will have to find out the frequencies. So lambda equal to omega square. Omega is nothing but 2 pi f the whole square. 2 pi f the whole square, 2 square is 4 pi f1 square. So lambda 1 equal to 4 pi f1 square, or f1 square equal to lambda 1 divided by, if this 4 pi goes to the other side, you will get lambda 1 by 4 pi, or f1 equal to square root of lambda 1 by 4 pi. And similarly lambda 2 will be, if you are just trying to rearrange it, you are going to get f2 equal to square root of lambda 2 by 4 pi. So the value of f1 is lambda 1. Lambda 1 is, earlier whatever the value I have got, I have put it, but you can just put the current value. So once you are trying to put that, say I have put the earlier value divided by 4 pi and square root of that. First you can put this in the calc. For example, let me just try to show that. So let me reset this. So let me just try to show you that as well. So let me put it 1.0. So let me open the brackets. 1.06 into 10 to the power of 10 divided by 4 into pi. So it is nothing but like you are getting like this. So square root of answer, I'm just going to put like the square root of answer, I'm getting 29,043. So 29,043 hertz, that's what is f1. Similarly, if you're trying to put, you're going to get f2 as well. So this is how you're going to find out the eigenvalues and its frequencies. Next, let's try to find out the eigenvectors.